مو مفهوم.
Sorry, I forgot to unmute my microphone. Yeah, I'm showing you myself only briefly. I will switch off the video, the camera, because it can cause some trouble. So just that you see that it's me talking live and not listening to a pre-recorded session. Okay, so camera away and full screen. We start today with the discussion of errors in CFD. I indicated last time that the issue of error analysis is very important because, first of all, the solutions from numerical methods are always approximate solutions, they are never exact. And on the other hand, the user who uses a CFD tool can make a number of errors, so it is very important to check and make sure that the solution that one is obtaining, presenting, and using is really as good solution as one can obtain, and this is appropriate for the particular application. So, as already said, numerical solutions are always approximate, and they include both systematic and avoidable errors. Systematic errors are those that you can't avoid, they are always there, and one can take measures to try to control them, to estimate them, and so on. And avoidable errors are errors that users of CFD tools can make, like with any tool, and these are also needed to be controlled. So one has to examine the solutions to check whether one has made any error or not. Systematic errors are of three kinds. First, modeling errors. This is the difference between the real flow and the exact solution of the mathematical model. So if you are solving Reynolds-Everett-Navier-Stokes equations with a turbulence model, that would be the difference between exact solution of these equations, if one was able to obtain them, say analytical solution, and the real flow. Of course, there is a problem that we don't know, can't obtain the exact solution, and we also don't know the real flow, but if we had these two information, the difference would be the modeling error. Because if equations are not exact, then of course the solution will differ from the real flow. Then the next level is discretization errors. That's the difference between the exact solution of the discretized equation of our mathematical model and the exact solution of differential equations. So there is a difference between equations in their original form as partial differential or integral differential equations and the equations which we obtain through discretization process on a given grid. And when we get exact solutions of the discretized equation, compare it with the exact solution of differential equation, there would be a difference, which obviously becomes smaller the finer the grid is. But this is what we call discretization error, and this is one of the major sources of errors, and one that we need to control usually by grid refinement studies. And then the third level are iteration errors. And this is the difference between the exact and the iterative solution of the discretized equation. So as you see here, we're going from top to bottom, and this is also the order of the level that you would like to have. You would like to have discretization errors smaller than modeling errors, and iteration errors smaller than discretization errors. Iterations errors also include round-off errors due to finite arithmetic accuracy of computers. Very often, when you use a CFD code, you can choose whether you want to use single precision or double precision, or some codes offer mixed precision, like SimCenter StarCCM Plus. It has only two versions. One is the mixed precision, which means that some variables in the code are treated as double because they are considered sensitive, and other variables are treated as single precision, which then saves a little bit on memory. And then when the results are saved, they are saved in single precision, which means 6 to 7 significant digits. And the rest is then forgotten. I always use double precision, which means that all variables are in double precision, something like 14 to 15 significant digits. For reasons that I have encountered every now and then, that the other version doesn't converge, where double precision version would converge. And the computing time with modern processors is more or less the same, so one doesn't save much computing time if one uses single precision. The only difference is that the file size is doubled. So if you perform simulation in double precision, you are saving also data in double precision, and the files are then twice as large. But in most cases, this is not a problem. Okay, and there are avoidable errors, as I mentioned earlier, and these are of two kinds. One is the programming errors. So the codes usually have bugs. Somebody said every code has bugs, which is probably true for a bigger codes, and they are usually difficult to spot. So nobody makes programming errors intentionally, but sometimes bugs remain in the code for many years before they are discovered, because if they don't show obvious misbehavior of the code, then the developer thinks that it's okay. The user doesn't see any problems until something happens, some application where the bug shows up, and then usually bug is reported to the software vendor if you're using commercial code, and it gets removed. If you are using code that you wrote yourself, then you have to try to solve the problem yourself. And there are user errors. Every CFD code is actually a tool like any other tool, and the user can make errors with it. The usual errors that the users can make are mixing up units in geometry. You get the geometry from somebody, let's say CAD model, and in CAD model the unit is inch, and you assume that it's meter. Most codes will assume that geometry is everything is in SI units. So length is in meters, time is in seconds, mass in kilograms, and so on. So if data is entered wrongly, that causes an error. One may also provide wrong fluid properties. Usual problems with user errors are boundary conditions. If you don't set up boundary conditions properly, then you will probably get a right solution, but to another problem, not the one that you want to solve. And also users can make errors when interpreting the solution. So you may have the right numbers computed by the code, but when you interpret them, you can make an error and make a wrong solution wrongly presented. So these are problems that one needs to bear in mind, that they can happen, and it is therefore important to carefully examine the results, not just look at numbers like, let's say, force or heat flux or some integral quantity, but also always check the flow features. So look at velocities, pressure, temperature, whatever, you compute it in several cross sections, make isosurfaces or whatever, just to make sure that the solution is plausible and qualitatively as expected. So very often one makes error, which if you look at integral quantities like force or heat flux, you may not see it, it may look okay, but when you look at the full information, you will spot probably there was an error somewhere. Now let's talk a little bit more about modeling errors. I mentioned already one reason, and that is that equations being solved are not an exact description of the flow because models are used which are affected by assumptions. So we know that, for example, Navier-Stokes equations describe most Newtonian flows of Newtonian fluids accurately. They are also not exact. There are some approximations also in the derivation of Navier-Stokes equation, but for engineering purposes, they would be more or less accurate, more than enough. The problem is that for turbulent flows, we usually have to use some kind of turbulence model, so we don't solve directly Navier-Stokes equation. That would be called direct numerical simulation. We usually solve either large eddy, detached eddy equation, detached eddy simulation version, or we solve Reynolds average Navier-Stokes equations, and these contain models. So even if the equations could be solved analytically, the solution would not match the reality. But there are also other sources of errors, and we can list all of them in the next slides. Turbulence models remain one of the major sources because almost every engineering flow is turbulent. Whether you have other models involved is another question, but turbulence models are usually always there. And every turbulence models involves some assumptions, and some empirical data is used in terms of some constants, which is also not universally valid. But there are other models, as I mentioned earlier, like if you have a multi-phase flow, the simplest one would be the free surface flow around the ship. So you have water and air. That also involves an additional model, which is then included in the equations. If you have chemical reactions, like might be electrochemistry, might be burning something or so, that also includes an additional model in the equations, and all of these models will make solution differ from the reality. Then there are approximations in boundary conditions, because in many cases we don't know exactly what to apply at the boundary. At inlet we must prescribe everything, but very often we only know the flow rate or something like this, mean information, but we don't know the exact distribution of velocity. So we often specify constant velocity at inlet, where in reality it is not constant. Or we don't know what to specify at outlet, so we set just extrapolation with, let's say, zero gradient, which is also not exact. Or in the far field, if we are looking at the flow around airplane or car on the road, we can't go to infinite distance from the body, so somewhere we will have the outer boundary, far field boundary, and we have to specify something there, which is also not exact. So all these imperfections of boundary conditions also contribute to the modeling errors, because we are solving equations for wrong conditions. Then the next source of modeling errors is simplification of geometry. Very often we have some small features which we intentionally omit from the grid because it's too complicated and we assume that the effect is small. Then there is uncertainty in tolerance. I will show later an example of measurement of real geometry of a propeller and comparison to the CAD model. Because when you manufacture something, it is not exactly the same as what the CAD model was. And of course, when we do simulation, we take the CAD data. So the geometry, let's say if I take the propeller, from a CAD model, then every blade is the same and everything is perfect. But when you manufacture propeller, every blade is different, and there are certain deviations from the CAD, and this is another source of error because we are not doing simulation for the real geometry. Then often users of CFD codes compute only half of the real flow domain and apply symmetry condition in order to save computing time, memory. And people assume that if the geometry is symmetrical, the flow will also be symmetrical. But this is very often not the case, and that can result in significant errors, and I'll show later an example. In most cases, the flow at high Reynolds number is not symmetrical because symmetry is, as the Reynolds number increases, unstable. And for example, in diffusers, in most cases, you will get something which is quasi-stable, quasi-steady flow, but asymmetric. On one side, you have larger recirculation than on the other. Maybe on one side, no recirculation, and only on one side recirculation, and so on. And if you have bluff bodies, then you will always have behind bodies vortex shedding. So this is not turbulence, but it also exists in laminar flow under laminar conditions. But this there is no symmetry in the flow. It's symmetric geometry, but the flow is asymmetric. And then there is also uncertainty in fluid properties because they often depend on temperature, maybe on pressure and concentration of some species. And this dependence can also be significant, but very often we simply pick from literature some mean values of, let's say, density, viscosity, and so on, and this introduces an additional error. So here's an example of a modeling error. If you want to simulate flow around a cylinder in a channel, let's say you have a channel with a rectangular cross-section, and then you have some cylindrical obstacle which goes from one wall to the opposite wall. And in this example here, I'm solving for inviscid flow. And this is and the simplest mathematical model of the flow, assuming that it's inviscid, it's potential flow, so to say. And in that case, the result by solving these equations exactly would be a symmetric flow left and right of the cylinder. So you have high pressure, the flow is here from left to right, as you see from velocity vectors. So you have stagnation point on the left at the symmetry. That's where you have maximum pressure. You have minimum pressure at the top of the cylinder, where the velocity is maximum. You can see the correspondence between velocity and pressure, where velocity goes to zero, pressure goes to maximum, where velocity is maximum, pressure goes to minimum. And then on the back side of the cylinder, the pressure should recover and be the same as on the front side. Here you see that it's not exactly the same because numerically it's very difficult to get this perfect symmetry because of discretization errors, but it is kind of symmetrical. And the consequence of this symmetry of the solution is that there is no force on the cylinder. So when you integrate pressure around the cylinder, you get zero force. That's the famous D'Alembert's paradoxon. In an inviscid flow, there's no resistance, and also this makes the flow to be totally unrealistic. So this is a very large, by solving inviscid flow, you create in most cases very large modeling errors, which is why we don't do it that way. If we now solve the Navier-Stokes equation and we choose the fluid properties and velocity such that the Reynolds number based on cylinder diameter is 100, but we say, okay, we will, the geometry is symmetric, so we'll compute only half of the domain. Then we will get flow as you see it here in the pictures, pressure on the top and the velocity is at the bottom. The front side is similar to the inviscid flow. You have maximum pressure at the stagnation point, and then acceleration of the flow, minimum pressure at the top. But then in the back there is a large recirculation because viscous flow will then separate from the cylinder surface, and you will get recirculation behind the cylinder. Now this so far looks good, but the problem is that in reality the flow will not be symmetric, and the real flow will look like in these pictures. So if you have a bluff body, then usually you cannot assume that the flow will be symmetric. You have to solve for the whole geometry, and then in most cases you will see that the flow is not, there is no steady state solution. We'll talk about it later, and you have to compute this as unsteady flow. And then you will see, for example, in this particular case, that this vortex behind cylinder will move downstream, another vortex will be built. There is a periodic oscillation of forces, and this is the information that the engineer would need to know. And if you assume symmetry, you make again a huge error, because this is not the reality. And in many cases, the oscillation of the forces would be a cause of concern, because they can cause mechanical failure, they cause more noise, they can cause vibrations, and so on. Okay, let's now discuss discretization errors a little bit deeper. They depend obviously on numerical grid, and the properties of the grid which influence discretization errors are type of the grid used. I will show later an example with tetrahedral, hexahedral, and polyhedral grid. In general, no matter which grid type you take, if you do systematic grid refinement, on a very fine grid you should always get the same solution. So it doesn't matter so much which grid type you use if you can afford to make very fine grid. But on any given grid with a given number of cells, how big the error is will depend also on the type of the grid. So if you have, let's say, 1 million cells in the flow around the ship, you will most probably have largest errors with tetrahedral grid, and then the other two, it depends how you locally arrange it. Tetrahedral will most probably have larger error. Then the next grid property which is important is the grid quality. If you have a general grid in complex geometry, there is non-orthogonality, there is skewness, there is aspect ratio, and so on. We will talk about it in more detail in another lecture. And you can have the same number of cells or grid points, but depending on the property of the grid, how these are distributed, you may have errors which differ by an order of magnitude. So grid quality is an important factor. And then, of course, grid fineness. That means the number of cells that you have. So if you have a good grid, nicely designed, high quality of cells, then you affect the discretization errors by increasing the number of cells or decreasing the number of cells. And then, of course, even if the grid quality is good, the local refinement and the distribution of the cell size can make a big difference, because you may have 10 million cells in two grids, but one may be adequately locally refined where it's critical, and left coarse where it's not critical, and the other one may be more uniform so that it's not fine enough in important regions and finer than necessary in other regions. So when somebody tells you, I did simulation with certain number of grids, that doesn't say much about the quality of solution, because if the grid is not well designed and locally refined where necessary, even if it's of good quality and has many cells, it may still have large errors. So this is another important aspect of the grid. And then, of course, for any given grid, the approximations which are used in discretization process make a difference. How are surface integrals approximated? In most computer codes that you will likely use, commercial codes, it's midpoint rule, so it's a second order approximation, and there is no choice. So whether you use OpenFOAM or Star CCM Plus or Fluent or any other code, there is nothing to choose here. But if you're writing your own codes, you could make a difference. In 2D, for example, you could use Simpson rule for integral approximation, which is a fourth-order approximation, which would be much more accurate. Then approximation of volume integrals, again, most commercial codes use midpoint rule, which is a second-order approximation, which means that the value at the center of the volume is multiplied by the volume, and that's the approximation of the integral. Then there is interpolation to compute variable values at location other than certain centers. And the most important of these is the interpolation to phase centers. That's what you need to compute convection fluxes. And this interpolation is one of the major sources for discretization errors. Many codes have options here to choose from. Almost all codes will have upwind differences of first order, which is not so good because you have larger discretization errors, or something that's called numerical diffusion. But then there are usually second order schemes like linear extrapolation from the upstream side, or linear interpolation, which is called central difference scheme. You may have also quadratic interpolation, quadratic upstream weighted, or quick is called in some cases. And you may have also some other more exotic interpolations. But these are very important. One often uses upwind biased interpolation for steady state flows, but for large eddy type simulations, when you want to resolve in space and time turbulent flow more accurately, then centered scheme, central difference linear interpolation is more appropriate. Then there are approximations of gradients, which are also important. For diffusion fluxes, we need gradients at cell faces. So we need the derivative of the variable in the direction normal to the phase. For all scalar equations and for momentum equations, we also need derivatives in the tangential direction. That can be approximated in different ways, and that also affects how big the errors are. Depending now on the Reynolds number, the importance of convection and diffusion fluxes can vary. So usually at high Reynolds number, convection is more dominant, so errors made in interpolation is more important than in gradients. In the case of highly viscous flows, it will be the opposite, that gradients will be more important. One also needs gradients at cell centers, especially when you use turbulence models, because they often look at the gradients of velocities to compute, let's say, production of turbulent kinetic energy and so on. And then, of course, approximation applied at boundaries. If you apply Neumann boundary conditions somewhere, how you approximate gradient at the boundary and so on also affects discretization errors. Now, we come to iteration errors. So we have to do iterative solution because equations are nonlinear. Navier-Stokes equations and Reynolds average Navier-Stokes equations are nonlinear, so we cannot solve it in one way, in one go, even if we use some direct solvers. But then also, when we solve iteratively, and if we solve sequentially one equation after the other, as I sketched here in this flow diagram, we would usually linearize the equations, and then we will apply linear equation solver to linearize the equation for, let's say, u velocity, then for v velocity, and w velocity. And then we'll go to pressure or pressure correction, and then we go to scalar quantities like K and epsilon if you're using such turbulence model, temperature. And so every of these equations is linearized, which means that only the variable we are solving for to power 1 is considered as unknown. All other variables or any nonlinear version, let's say squared of velocity, will be split as a product of unknown value and a known value, so that we have linear equation, and this linear equation is solved then using some linear equation solver, which is also iterative. One could theoretically use direct solvers, but that would be too expensive and unnecessary. So we have to apply linear equation solver, and we stop iteration at some stage. And then we go and repeat the loop of solving all equations one after the other. because when we do these so-called auto iterations, we will update the matrix coefficients and we will update the right-hand side of the equations and then repeat the whole process. So there are out iterations, in iterations, and for each of them, we have to decide when we stop iterating, because obviously if you iterate until you reach round off level, you will get the most accurate solution, but it is more accuracy than necessary. Nobody needs 15-digit accuracy, because discretization error may be of few percent, and modeling error may be also even larger. So there is no reason why one should iterate on a given grid too far. And the question is, when do we stop? We will talk about it a little bit later, but I just want to stress here that there are two kinds of iteration errors, and we have to specify convergence criteria for both of them. Now, there is also a problem for engineers using CFD, that errors from different sources interact with each other. And the total error, which is the difference between real flow and the numerical solution, depends on this error interaction. So you may have, for example, the situation where the errors augment each other and make the total error very large, so you may be discouraged from doing simulation at all because it's a big error. But then when you refine the grid, it may happen then that the error reduces very rapidly. In another situation, you may have the case that errors cancel each other, partially or to a large degree, and the error can be low even if the total error can be low even if the individual errors are high. So for example, you can do the simulation on a relatively coarse grid and you compare your results with experiment and you find out that they agree very well, but maybe the modeling error is very large, but it has one sign, and discretization error is very large, but it has the other sign, and they partially cancel out and everything looks good. And then you go and refine the grid, because that's what I'm telling you, that you need to refine the grid to check the discretization errors, and all of a sudden, as you refine the grid, the difference between solution and experiment becomes larger and larger. And this is then the sign that some errors are partially canceling out. It would be wrong to conclude that the coarse grid is better than fine grid, because by definition this is not the case. But the errors may, as I said, partially cancel out. And also, if you do simulation of the same problem on the same grid with two different codes, as I've seen this week in another project, you may see that, for example, in one code, when you go from grid 1 to grid 2, the solution changes in one direction, and you grow from grid 2 to grid 3, and then the difference is again back in the other direction, so that, for example, grid 1 and grid 3, although they differ by factor 10 in resolution, may have very similar solution. And the other code will have monotonic variation always in the same direction, and the difference between first and second grid is much larger than between second and third grid. So this is also possible that because of these different errors and different interactions between errors. So it's therefore important to analyze each error type independently and try to estimate the contribution of it to the final solution. Because, as I said, you may get the total error small for the wrong reason. You get right solution for wrong reasons because errors cancel out. And one should always aim to obtain solution with error levels which are sufficient for particular applications. Sometimes 10% error is okay because you are maybe doing design study, you want to find the optimal design, and then you don't need most accurate solution on every grid because you'll do hundreds of grids. You want to see which one is better, and for this it doesn't have to be too accurate. And then later on, when you come close to optimum, you then do more accurate simulation. But there are some applications in which 1% error is too much, and one has to try to do even better than that. I mentioned here under relaxation because it happens, it is important later on when we talk about iteration errors. What under relaxation means is that we don't take the solution that the discretized equation would give if we solved this discretized equation exactly. We mixed that solution that the equation would give with the solution from previous iteration. So if you have an algebraic equation at one cell, P denotes the cell center, so there is a coefficient multiplying unknown at cell center plus some of the coefficients multiplying unknowns in the neighboring cells equal right-hand side. So if I solve this equation accurately, it's a equation system, you have to take into account all cells, but in the end, when you have an accurate solution at the cell center, as all terms on the right-hand side, that would be the new solution if the equation is solved accurately. We say, no, we don't want that. We don't want to go that far from the previous solution. We want to slow down from one iteration to the other because if you have this segregated solution and because of some approximation being made, divergence happens. So say I want the solution at the next step to be the solution from previous iteration with superscript n plus the difference between the two multiplied by an under-relaxation factor. In other words, you will take alpha phi contribution of the new value and 1 minus alpha phi contribution of the value from previous iteration. And when this is built into the equation itself, before solving it, then you get the modified equation, which is the one that we solve. The central coefficient is divided by under-relaxation factor, and on the right-hand side, you have an additional source term, 1 minus alpha phi divided by alpha phi times AP times value from the previous iteration. So this is how we, so to say, apply the break, and we say the new value should contain contribution from the value from previous iteration and not go as far as the equation would like. This can be also interpreted as marching in a pseudo time, because if you take equation which is discretized for unsteady problem, and which is here the second in this, where we have two equations. So the first one is the steady state equation with under relaxation. The second one is unsteady equation. So we have, in addition to AP, which contains contribution from convection, diffusion, and sources, we have contribution from time derivative, and on the right-hand side is the contribution from the old value from previous time step. And if one makes these two equal, you will see that using under relaxation is equivalent to marching in time, but the time step is then different from cell to cell. So if I use the time step to march in time, it's equivalent to using an under relaxation factor which varies from cell to cell. This is the possibility. So you can apply transient unsteady computation always, and if there is a steady state solution, you will reach it by marching in time. And if you know that there is a steady state solution, you can ignore time derivative, but then you have to apply under relaxation, and then you go towards steady state. And I will show later on how the discretization errors or how iteration errors depend on these under relaxation factors, because if you apply too strong break, then it takes longer, obviously. And here is the example. If I want to solve the flow in a lead-driven cavity, this is something that is very often used to demonstrate features of numerical methods. So you see here at the bottom right corner a square cross-section. So for 2D problem, it would be just a square. For 3D, it would be a cube. And the top lid is moving. And because of viscosity, it's driving the flow inside to also rotate. And then you have vortices in the corners. And if I now solve this laminar flow at Reynolds number 1000 on a relatively coarse grid 32 by 32 control volumes and vary under relaxation factors, then you get the picture on the left. So if I have a low under relaxation factor for velocity, let's say 0.5, then under relaxation factor for pressure, which is shown here as the bottom axis, can be anywhere between 0.1 and 1. It won't make a big difference. You always need something like 530 iterations to reach the solution, which means that I'm under-relaxing velocities very strongly, and pressure doesn't matter so much. Here is a simple algorithm used, I should have mentioned, for those who know what it is. And then if I now increase the under-relaxation for velocities and go to 0.7, then I need much less iteration, less than a half, only 230 to reach the same convergence criterion. And now I cannot use under-relaxation larger than 0.9 for pressure. And if I go below 0.2, then the number of required iteration increases. And then if I go to under-relaxation for velocities of 0.8, now I cannot increase under-relaxation for pressure beyond 0.5 or 0.6. 0.6 is the maximum value. But if I am somewhere in the range between 0.2 and 0.5, I need now again much less iteration, only something like 140. But the range of under-relaxation for pressure is much narrower. And then if I go to under-relaxation for velocity of 0.9, I get a single point with optimum convergence, just a little bit more than 100 iterations. And then if I increase under-relaxation for pressure, then very rapidly it will diverge, so I can't go beyond 0.25 or something like this. If I reduce under-relaxation for pressure, then number of required iteration increases. And there is in literature also expression for optimum combination of these parameters, which typically says under-relaxation for pressure should be 1 minus under-relaxation for velocity, which is roughly correct if you look at it here. It's not necessarily always the optimum, but it is kind of reasonable. On the right-hand side, there is the same flow, but now many different grids, from 32 by 32 up to 256 by 256 control volumes. Okay, this is now German label, KV for control volume, rather than CV in English, but I think it's not a big problem. So you see here it was iterated to a much tighter tolerance, and under-relaxation for pressure was always under-relaxation for velocity minus 1 minus under-relaxation for velocity, or something close to it. And you see another important factor is that the finer the grid, the more iterations one needs if one is away from the optimum. So let's say typical values for default values, if you take computer code, it will probably, if you want to solve steady state, it will have default under-relaxation for velocity 0.8 and for pressure 0.2 or 0.7, 0.3. And you see that this is very far from the optimum. With 0.8, and here very tight convergence tolerance was used, so I think residuals reduced 5 orders of magnitude. But you see for 0.8, one would need many thousands iterations to, maybe probably 8,000 iterations. And if I take 0.95, it's 2,000. So it's factor, more than a factor of 4 less than the default value. So if you, the point here is, if you need to do many simulations of similar flow, then it's probably worth to see what is the maximum under-relaxation that you can use, because the default is usually relatively conservative, and one can save significantly computing time by using optimum. And you see here on a very coarse grid, it doesn't save you too much, but the finer the grid, the more saving one can achieve. Now, how do we estimate iteration errors? And to see this, we have a look at the residual, because this is something that we need to compute in the process of solving equations. We want to solve the equation which is written here. A is the coefficient matrix, phi is the unknown, and q is the vector of right-hand sides. And we do an iterative solution. So after n iterations, we have solution phi superscript n, and because it's not the exact solution of the discretized equation, there is a residual rho sub n, so equation is not exactly satisfied, there is this residual. If I subtract the solution after n iterations phi n from the exact solution, I get iteration error. So when I iterate to round off level, then I can assume that this is exact solution, and difference between solution at any iteration and this one is the iteration error. But when I subtract these two equations from each other, then I get an equation for iteration error, which says that I can compute iteration error using the same equation if I use the residual on the right-hand side as the source term and the same matrix. So this is the relation for linear problem, and which tells us that there is some kind of proportionality between iteration error and residual error. So if this was a one equation, then you would say, of course, the proportionality is 1 over A, but A is here matrix, so it's not that simple, but in any case, these are proportional to each other. And because we need to compute residual in every step anyway, we can use the residual to determine when to stop iterations. How this is done is not so straightforward, because, as I said, you don't, when you see the value of residuals, you don't know how big the values of iteration errors are, because you don't know the scaling factor. Unfortunately, there is a property of these two that one can use. So, but one needs to distinguish these inner iterations and outer iterations. And the inner iterations, we repeat these inner iterations in every outer iteration. So usually we don't need to solve accurately linearized equations. And the typical convergence criterion is 1 order of magnitude reduction per outer iteration. In some cases, when you have stiff problems, you need to adjust these default values to a tighter tolerance, but usually if you use commercial code, you will seldom change the convergence criteria for inner iterations. For outer iterations, this is what matters, because if the residuals of the equation are small after you update the matrix elements and right-hand side, then you solve your nonlinear equations with a given accuracy, and that's what's important for discretization, for comparing iteration errors to discretization errors. Now, how can we determine exact iteration errors? I mentioned earlier, if we once iterate until we reduce residuals to round-off level, that provides us the most exact solution that we can obtain. So it's not exact in the sense of analytical solution, but we can't get it more accurate because the computer doesn't have more digits, but it's usually more accurate than necessary. As I said, for most engineering applications, 3 or 4 digit accuracy is more than enough. But if you obtain a solution with 15-digit accuracy, that can be considered exact. And now we can repeat the computation, and after every iteration, we can subtract the intermediate solution from the exact one, and then we have the exact error. More or less, it will only be wrong when we come close to the last iteration near round off, but in the initial phase, this difference is really the real error. And this is something that one needs to do when testing a new code. So when you do validation of a code, you have to do it once or twice to just see how it behaves. And these inner iterations must always be reducible to round-off level. So if this is not possible, then there is some bug either in the code or in some conditions. Outer iterations must be reducible to round-off level if you are solving a transient problem. Then within each time step, if you iterate long enough, you should reach round-off level. But you usually don't go that far because, as I said, 3-4 digit accuracy is sufficient for engineering applications. So we will stop iterations earlier, but if you want to make sure that the code is working properly, you have to check it, as I said, once or twice to ensure that it does go to round-off level. But when you're solving steady-state problems, then things are different. Auto-iteration errors may not be reducible below a certain level, depending on the flow. What that indicates, well, if there is an error in the code or boundary conditions, then that would be one reason why residuals don't go below. But even if everything is correct, if the flow is inherently unsteady and you're trying to get steady-state solution, that won't work. I show an example later where simply residuals oscillate because the flow has unsteady features, something like vortex shedding most probably. And now this settling of residuals, when they don't go any further, can happen at different levels. So if you're computing flow around, let's say, a car, and you have many, and you resolve everything, the mirror, the spoilers, the windshield, the wipers, and everything in underbody, brakes, and so on. There may be vortex shedding somewhere, but because that part of the solution domain is relatively small, it doesn't contribute too much to residuals. But when you get to sufficiently low level of residuals, this will become important, and then residuals don't go below that level. And then it depends on what you are looking for. If you're looking at the resistance, the drag, maybe that small part of the flow which has vortex shedding doesn't contribute to resistance too much, and you can accept solution in which residuals have stopped reducing, let's say at the level of 10 to minus 4. They are normalized properly, and that may be accepted as steady-state solution. But if the residuals start oscillating at a high level, then you have to switch to unsteady simulation, and then you will see how the flow varies in time, and then you can do averaging, but this is then important to recognize that the problem is unsteady. Now, sometimes you can get steady-state solution when you do simulation on coarse grid, but you refine the grid and you don't get steady-state solution. Why? Because coarser grid introduces something that we will later mention as numerical diffusion, and it basically effectively reduces the Reynolds number. And that means that with this additional numerical diffusion, the flow may become stable and you get steady state. And once you refine the grid and reduce this numerical diffusion, then your Reynolds number becomes closer to reality and the flow becomes unsteady. Then you have to switch to unsteady simulation again. Here is a plot or two plots of variation of iteration errors for a particular linear problem. So any linear equation will behave similarly. In this particular case, I was solving simply Laplace equation. So once you discretize Laplace equation, there is no need to change coefficients and right-hand side. So it's all done in one go, and then you only need to solve this linear equation. There is a way to estimate iteration error, which I will not describe here. It's in my book. If somebody is interested, Computational Methods for Fluid Dynamics by Ferziger, Berich, and Street, you can find how this can be done. And we compare here estimate of iteration error, the exact error determined as I described earlier, once iterating to round off and then subtracting solutions at each iteration from it. Then one line is the difference between solutions at two consecutive iterations, a norm of it, and then the last one is the residuals. So the norm that I used here was sum of absolute values. So you take absolute value of residual or absolute value of the difference between solutions at two iterations at the same grid point, and then you sum it over the whole solution domain. No other normalization. And if we look at these curves, what is interesting is that they are parallel. The estimate becomes exact after 200 iterations and matches the real error, but it is wrong at the very beginning. And this is also not surprising, because in order to obtain this estimate, you need to have some information from the flow, and usually when you start solution, you start from some guess, in this particular case for 0 values, and obviously this is very wrong. So after a while, estimate can be good. You see that the residuals and the difference between solutions to 2 iterations is much lower, 2 orders of magnitude or even 3 orders of magnitude below the real error. But the slope is the same. And that what that means is, if I now go backward, let's take the residual, the lowest line. If I go backward from the last point and extrapolate to iteration 0, I see that I have roughly 3 orders of magnitude reduction in residual level, and this is also the same you would get from error. The residuals dropped very fast initially, and this initial reduction is not proportional to the error. Error reduces smoothly from the beginning. There is no this sudden drop, but the residuals reduce too quickly. So if I stop the simulation after residuals drop 2 orders of magnitude, that would not be enough, because error has reduced only a little bit. The left picture, which is so nice, is when you use linear equation solver, so-called over-relaxation method, and we use over-relaxation factor which is smaller than optimum. Then everything is smooth. If I take the over-relaxation factor larger than optimum, what you see on the right-hand side is that I need then less iterations to get the solution, not 1,000, but less than 300 for the same level of error. No, actually for the same level of residuals. The error is on the left still much larger. On the right, you see that the error is also reduced 1, 2, 3, 4, 5, 6 orders of magnitude in 280 iterations. But the behavior is not so nicely monotone. There is some strange sudden drop in residuals and in this difference. But still, you can see that there is a correspondence between the behavior of the residual and the behavior of the iteration error, and that means we can judge when to stop iterations, both inner and outer, by looking at the residuals and requiring that the residuals are reduced, let's say, 3 or 4 orders of magnitude. And usually we also then monitor the variable values at some location which we think will be sensitive, and then we see whether this variable is now changing or not changing, and we often also look at integral quantities. But residual is usually one of the major ways how to judge when iteration errors are small enough. The difference between solutions of 2 iterations can be small if the solver converges slowly, so it would need to be normalized to get the error. But again, if you require that this difference is reduced certain number of orders of magnitude, that is also acceptable as much as the residual is, as these examples here show. Now, this was the previous example was for linear problem. We can do the same for nonlinear problem for solving the fluid flow. Here we are again back at the lid-driven cavity. The picture on the right shows the grid and the streamlines. And on the left, we have again the same thing, the iteration errors determined by ones converging to round off and then going back and subtracting solution from the exact one. Then there is an estimate of the error, which is the line below. And then there is the difference, again, between solutions of 2 iterations and residuals. And here, again, we see, as in the previous case, that residuals reduce initially much faster than the error itself, and later on the slope becomes the same. So again, by extrapolating backward, you can estimate how many orders of magnitude has the error been reduced, as you see how far the residuals have been reduced, but you have to usually neglect this initial phase if it's so sudden as it was here in the case. And I mentioned one should always, for a computer code, test whether it will converge to round-off level. And here is an example, laminar flow around circular cylinder in a channel with symmetry condition, which is the wrong physically, but for computational purpose, it produces steady state flow. So it's a correct solution, but for imposed symmetry, which you can't impose in reality, but if you could, you would get that solution. We see that the residuals initially very irregularly, so they drop very quickly, then for a while they are constant, even increase a little bit, and then after 120 iterations or 140, then they start reducing at a constant rate. And this constant rate stays until you reach round-off level. And here, of course, you could now, you see, you could extrapolate linearly from the back to the front, and you see how far the errors have been reduced. So I'm now sure if I reduce the residual 14 orders of magnitude, that also my iteration error has been reduced at least 13 orders of magnitude or 12, but anyway, 12-digit accuracy is far more than necessary. But it's important to make sure that it's possible to get that far. Now, here we look at the iteration errors for unsteady problems. So this is flow around cylinder in a channel, and cylinder is positioned asymmetrically. It's closer to bottom wall than to top wall. And here again, inside one time step, I can do the same. I can converge iterations in one time step until I reach round-off level of residuals, save the solution, restart again at the beginning of this time step, and then subtract the solution at every iteration from the saved final solution. And in one particular time step, the diagram, upper diagram on the right, shows the error, which is blue line, and the residual, which is red line. And you see that they are, again, parallel. The residual reduces initially a little bit faster than the error, but later on they are parallel. And the bottom diagram on the right, I show here again the effect of under-relaxation factor. So this shows only the residuals. And what is here visible is, okay, here errors, this shows error on the left, but this is, I think, the residual. Although I'm not now 100% sure, it's not normalized. So in the upper picture it is normalized, so you have small values. Here it is not normalized, the values are larger. But anyway, it's not so important. What is important is that if you have larger under-relaxation factor for velocity, the reduction is initially larger. Later on, it becomes, again, the same constant rate that we saw in the upper picture. And why it is important, if we don't need to solve outer iterations to a too tight tolerance in every iteration, because solution from one iteration to the next doesn't change very much. So if I reduce, so the error is already not very large at the beginning of the time step, and if I reduce it to 3 orders of magnitude, this is more than enough. That's why it is good to have large under-relaxation factor, because this initial reduction is important, and the later on is more than we need. But the behavior is similar. Now, in many simulations of unsteady flows, we even don't monitor the residuals, but prescribe a fixed number of iterations. And this has to be done with care, because in some cases, this is okay. 3 iterations may be enough. In other cases, the dependence may be much stronger, depending on what the problem is, how large the time step is, and how large are under-relaxation factors. So if you take the under-relaxation factor the same as for steady state, 0.8, 0.2, and you need more iterations than 3 within time step. But if you optimize under-relaxation factor for the particular problem, and here was this flow in the cylinder, you see in the upper diagram is drag. It varies aperiodically because of this fact that it's closer to one wall than to the other. And if I fix the number of iterations once to 3 per time step, once to 6 per time step, but increase under relaxation factor for velocity to 1 and for pressure to 0.5, then you see no difference between these two solutions. So whether I do 6 iterations, 3 iterations, you can't see it in the drag. And also in the lower picture is velocity profile behind cylinder from bottom wall to top wall. And you see negative velocity, that's recirculation behind cylinder in one part, and higher velocity in the other part. And again, the red and blue curve can be hardly distinguished from each other, which means that here with these under relaxation factors, 3 or 6 iterations is enough. I didn't plot this, but if I was using 0.8 for velocity and 0.2 for pressure, then the difference would be significant, and one would say that 3 iterations per time step is not enough. But there are some cases when you need more than 5 and more than 6. However, I always recommend that if you need more than 10 iterations per time step, then it's better to reduce the time step than to do 20 iterations, because the computing effort by halving the time step and number of iterations is the same, but the accuracy is likely to be larger, because for smaller time step, discretization errors are also smaller. Here is an example of the effect of under relaxation on convergence. This is a U bend, so it's a pipe with 180-degree turn, polyhedral grid. You have velocity field in the bottom, so at the bottom picture, the flow enters on the right-hand side and goes into the curve, and you can recognize some secondary flow. We'll talk about it in another lecture. And then at the exit of the U bend, you have higher velocity on the near outer wall and lower velocity near inner wall. If you take the under relaxation factor 0.7 for velocity and turbulence quantities and 0.3 for pressure, you need 400 iterations to reach residual levels 10 to minus 5. So 5 orders of magnitude reduction of residuals. So you see that the residuals reduce relatively quickly initially, so maybe error is reduced 4 orders of magnitude or so. If I now increase under relaxation for velocity from 0.7 to 0.9 and reduce under relaxation for pressure from 0.3 to 0.2, then I need only 140 iterations to reach the same level of residuals. Now 140 is roughly 3 times less than 420, which means that it is a significant reduction of computing effort. So if I'm doing some optimization study or need to do many simulations for different parameters for such a problem, then it is worth checking what is the optimum under relaxation factor and not use default values, because you save a lot of computing time. Here's the example that I mentioned earlier, where residuals don't go down as you try to do steady state solutions. So this is an obstacle mounted on a wall. This will be also, I think, looked at in the exercises. And this, you see in the upper picture on the left, pressure distribution. So low pressure on the sides where velocity is high pressure at the stagnation in the front surface. And the picture below shows velocity vector in one plane, horizontal plane above the ground. And you see that this recirculation is not symmetric. So the flow, there is, if I would put here symmetry plane and apply symmetry condition, then I would of course get symmetric solution. But in reality, this solution is not symmetric. There is some kind of vortex shedding. And below these two pictures on the left, there are residuals from the steady state computation above and from the unsteady computation below. So you see steady state residual started at about 0.1, increased initially, then decreased, and then it stays about the value of 0.1 all the time. So 5,000 iterations, no change. It's just oscillating around certain value. If I look at the drag coefficient, that's the upper picture on the right, I see the drug reduces to 0.275, then increases a little bit, and after 2,000 iterations, it oscillates around the value of 0.28. But because resilience is so high, this drug is not a solution. This is nothing that you can rely on, because equations are at no point satisfied. You always have large residuals, and so this is not a solution. If I now switch after 2,000 iterations to unsteady simulation, then first of all, I see that in each time step, all residuals are reducing. So here I think 5 iterations per time step were done. If I did more, they would be reducing even more. And this is a good sign. And now I do unsteady simulation. And the lower picture on the right shows now the variation of drug coefficient in this unsteady simulation as the iterations go. And you see I pick at 2000 where I stopped the steady state computation, and the drug very quickly increased substantially to value over 0.307 was, and then it's now oscillating a little bit, and probably likely to settle at about 0.305. And you see that this value is substantially larger than 0.28, that this not converged. I have seen people in industry sometimes doing steady simulation, specify number of iterations, and the residuals are not reducing anymore. They simply average the result. But in this case, it would be wrong. You would get an average of 0.28, and the real one is 0.305, and the difference is about 7% or 8%. So it means you'd make a big error. These slides were supposed to be at another location, and I had forgotten to add some text to it. Sorry, I'll edit them later on, but I can explain what this is. This is about numerical diffusion. You will hear very often in literature and in discussions this term numerical diffusion mentioned. What it is, it's a truncation error in equations or in approximations which has the form of second derivative of the variable times some coefficient. And because diffusion in the real equation has a second derivative times diffusivity coefficient, that's why this truncation error in approximation, which has the same shape as the physical diffusion term in the equation, is termed the numerical diffusion. And here we are looking at the convection of a step profile of some scalar variable, let's say temperature, in a velocity field which is constant. So constant field at an angle theta, which was here 45 degrees, and the grid is Cartesian. So as the picture on the upper picture on the left indicates, you have below a certain y coordinate, this variable phi is 0, and then the rest is 1, and then you simply convect it downstream. So ideally, without any diffusion, this step profile will stay the same. And if you have certain diffusion, and it will diffuse a little bit across the flow, but the simulation here was done with no physical diffusion, so all that we see here, all the spreading, is numerical diffusion. And the upper right picture shows the profile somewhere in the middle of the solution domain, so vertical profile along y coordinate, and phi goes between 0 and 1, computed using upwind differencing. That means first order approximation. We simply take the cell face value on the upstream side from the cell center. And you see, as I refine on a very coarse grid, already at half of the solution domain, this step profile has been totally smeared. The upper boundary, I don't have value 1 anymore. And then as I refine the grid, it gets steeper and steeper, but it is still very highly smeared. So numerical diffusion is very high because exact solution should be this step, the thin solid line. If I use central difference, which is linear interpolation between upstream and downstream point to get the phase value, then I get solutions which are shown on the bottom right. And what is here interesting is you see oscillations. The step is reasonably well resolved. Of course, it's better resolved on the finer grid than on the coarse grid, but it's much steeper than with the upwind scheme. So the step is resolved close to reality, but then because this sudden change from 0 to 1, linear interpolation with overshoot and undershoot, and you get this oscillation. And what is interesting is that the magnitude of oscillation doesn't really refine the grid. It stays similar, it's just that the wavelength, so to say, of these oscillations changes. It's always something like 2 or 3 cells, but you get these oscillations, and this is obviously not very good. Now, bottom left picture shows what you get when you blend 95%, I think, was of the central differencing, linear interpolation, and 5% of this upwind biased extrapolation, so to say. And you see then that the coarse grid also shows these overshoots, but they are not as large as with pure central differencing. The step is not as well resolved as with central differencing, but much better than with upwind. And here, what is good is if I now keep refining the grid, the amplitude of this oscillation reduces. And the finest grid tested here, 80 by 80, has only very, very small undershoot and very tiny overshoot, and the step is pretty well resolved compared with the upwind solution, the upper right, where the full line from 80 by 80 grid is still very far away from the accurate solution. So you see here an example how a blending of some low order scheme with high order scheme can help you to get rid of oscillation and get much higher accuracy than by using first order method. And many codes offer the possibility to blend two schemes. Usually one is upwind biased and the other one is more centered to affect the solution. And then this other picture, which I also I haven't have forgotten to write the text, shows the solution for lead-driven cavity, profile of horizontal velocity component on the vertical center line on the left, and profile of the vertical velocity component along the horizontal center line on the right, where solutions of 5 grids are presented from 60 by 16 to 256 by 256 control volumes. And what you see here, this is the classical grid dependence test that you would do. You see how the solution changes from grid to grid. The first grid is too coarse, so the difference between first and second grid is only twice as large as the difference between second and third. But from a second order method, which was used here, you would expect that this difference reduces by a factor of 4. And this is the case from between the next finer grid. So between third and fourth grid, the difference is 4 times smaller than between second and third, and so on. And solutions on 2 finest grids, you cannot distinguish in the plot. They fall on top of each other. On a second, with a second order method reduced by a factor of 4, and this is why you don't see. Okay, let's now see how the discretization errors can be estimated. Well, this grid refinement study that I've just shown is the only reliable way. We do know usually which order the scheme has. This order of the method relates truncation error to grid spacing, but it doesn't tell anything about the magnitude of the error. It only says what is the rate of error reduction when the grid is systematically refined. So second order method should eventually, when the grid is fine enough, reach the reduction by a factor of 4. This is 2 squared. So third order method will have reduction by a factor of 9. Fourth order method will have reduction by a factor of 16. But this error reduction rate is only achieved asymptotically. That means when the grid is fine enough. So coarse grids, error may even increase when you refine the grid initially and be reducing at a smaller rate, but then as you keep refining, they will be eventually reducing at a given rate. But how large the errors are, you don't know until you do something which will help you to estimate the error. And this is usually, as I said, this grid dependence study. You may have methods or schemes of the same order being used, approximation of the same order, but still the error may be order of magnitude different from that, because they may be reducing with the same rate, but the error will not be the same. Now, if you consider the whole equation, then we have different terms that are approximated using different methods. Each approximation has a different error, so the global error for the solution as a whole may not behave as may not have convergence or order which is an integer number. So you may get a formal order when you compute it to be 1.8 or 2.2 rather than 2 as you would expect. We'll show how this works later. So if you want to estimate discretization error using grid dependence study, then one condition has to be satisfied, and that is basically two conditions: that the refinement is substantial and that it is systematic. What substantial means is that the grid reduction factor should be larger than 1.5 roughly. You don't want to do a grid dependent study by reducing the grid by a factor of 1.1 because that doesn't bring much. So 1.5 to 2 is the usual, and that's considered as substantial. And systematic means that you don't change the design of the grid. So whatever the local refinements or whatever you apply to the first grid, this should stay the same, and you everywhere refine the grid by the same factor. Because if you change the design of the grid, refine it elsewhere, and change expansion or contraction factor if it's expanding also, then the effect of the change of design may be larger than the effect of the change of the grid size, and then it is difficult to draw conclusions. So good design of the initial grid is very important. And now how we can estimate the error? Well, first of all, if we would take the exact solution of differential equation and put it in the discretized equation, then discretized equation will not be satisfied. And this is symbolically expressed with this equation here, which is on the left-hand side. We have this calligraphic L of phi. Phi is the exact solution of the differential equation. This equal to 0 means the differential equation is satisfied. So capital phi is the solution of the differential equation. L sub h is the symbolic notation for the discretized equation on the grid with spacing h. And if I put the exact solution of differential equation into this discretized equation on a given grid, then I will get some imbalance, and this is the truncation error, which means if my truncation error was 0, then I would satisfy the exact equation, but because on a given grid, discretization error the truncation error is non-zero, then this is what comes out. If I now look at the equation which we solve, this gives us solution which satisfies discretized equation LH of phi h equals 0. That gives me the solution phi h, which is solution on a given grid, and that has a discretization error. And this discretization error on grid H, this is here shown as epsilon sub H sub D. D means discretization error. This error is the difference between the exact solution of equations and the exact solution on given grid H. Now I can subtract this equation from the previous one for a linear problem. If I assume that this operator LH, which is discretized equation, was linear, this is not true always, but as we iterate, auto-iteration continue, at some stage it becomes more or less behaving like a linear problem, so it can still be usefully considered. What this shows is that discretization error satisfies the same discretized equation with the source term being truncation error or minus truncation error. So we could actually compute discretization error from this equation if we knew the truncation error, but of course we don't know the truncation error, so that's the problem. This equation tells us nicely how one quantity depends on the other, but it doesn't help us to solve the problem. However, it's still useful because we can estimate truncation error by using the solution from a finer grid, putting it into the coarser grid and doing so as if it was the exact solution. Then the residual on the coarser grid would be an approximation of the truncation error. And then that can be now used to estimate discretization error. In most cases, this L operator is simplified, so you take only the central coefficient and you say that the discretization error is proportional to the estimated truncation error divided by center coefficient, which is called tau error. So this is one way of estimating the error, but the more reliable case is if we take solution on a series of grids systematically refined. And what we know is that the truncation error is can be expressed as some coefficient alpha times grid spacing to power p. P is the order of the method. So this is the leading truncation error term, and then there are capital H other truncation error terms, but we will neglect that for the time being. So we don't know what is this alpha, but we know that at a given point in space, it doesn't change as I refine the grid. So it's some physical thing. And so at any given point, if I refine the grid, what is changing is only the H, the grid spacing. The P is the order of the method, and alpha is the coefficient. They are not function of grid, they are only function of the physics. So they stay the same. And now I can express my exact solution of differential equation as the solution on grid H plus discretization error on grid H, which is what I've given here. And I can now use the same expression for coarser grids. So grid with RH, R is expansion factor. So if I'm using factor 2, it would be 2H or 1.5 with 1.5H. And then again, this forward discretization error is the same, only that now my spacing is not H, but is RH, but it goes to power P again. And if I coarsen the grid once more and I use the systematic refinement, then I have the same refinement factor on the next coarser grid, so it will be R square H. And now my error is alpha times R square H to power P. Now from these expressions here, if I take 3 grids, I can find the correct order, because as I said, it may not be exactly factor 2 if I'm using second order approximations, because there are different approximations for different terms. So if I take log of the difference between fine and the next coarser grid, medium and coarsest grid divided by difference between fine and medium grid, and divided by log R, I get P. And this P should be close to 2 if I'm using second order method. So this is important to do occasionally, just to check whether the order that you expect is also achieved. Especially important when you write your code yourself, because if you make an error somewhere and you think that you have second order scheme, you should get here P close to 2. If you get something like 1.1 or 0.9, then you know that there is something wrong and you need to look for a bug. You don't need to do it normally with commercial codes, because they should have checked it earlier. And now, if I know the order from these expressions here in the middle equation, I can compute an estimate of the discretization error on grid H as the difference between solutions on grid H and the next coarser grid, divided by the refinement ratio to power P minus 1. So let's say if I use refinement by a factor of 2, or coarsening, if I start from the finest grid, Then if I have a second order method, 2 to the power 2 is 4, minus 1 is 3. That means discretization error on the finest grid is equal to 1/3 of the difference between solution on the fine grid and the next coarser grid. If refinement factor is 1.5, then 1.5 to the power 2 is 2.25, minus 1 is 1.25. In that case, the error on the fine grid is roughly the difference between solutions on the fine and next coarser grid divided by 1.25, or roughly it's this difference. And this method of estimating grid discretization error is called Richardson extrapolation. And this you must know at the exam. Not necessarily writing the equation, but you have to know what it is and at least roughly what the expression is. Of course, if you have higher order methods now, for a fourth order method, for example, 2 to the power 4 would be 16, minus 1 is 15, so the error is 1/15. For the third order method, the error will be 1/8, and so on. This way of error estimation is accurate when the convergence is monotone, so the grid is fine enough, and it can be applied to integral quantities as well as to the field variables. And for highly transient flows like LES and DS, we can apply this error estimation only to mean quantities, to average quantities, and not to the instantaneous values, because they are random and they behave differently. When we do simulation of unstructured grids, this is still valid as long as the grid design is not changed. In Star Plus, you can design the grid and then refine it by just changing the base factor, base size, and then all grids are topologically similar, and then for a well-posed problem, you would still get this monotone convergence, and it should be suitable for Richardson extrapolation. However, sometimes we have complicated problems, like, for example, wall functions in turbulent flows that we will mention later, that are used to approximate wall shear stress at a wall, and some other things which have branches in the code. They make it sometimes difficult to apply Richardson extrapolation because this behavior is not exactly smooth as the theory suggests. But still, it's important to do grid-dependent study, even if you cannot strictly apply Richardson extrapolation. If you see that the difference between solutions on free grid is monotone and the difference between second and third grid is smaller than first and second grid, then you can at least roughly estimate how big the errors are, and you can then judge whether the solution can be accepted or not. Here's an example of a problem which is interesting for two reasons. One is that this was published in a journal, and when I saw the solutions, I knew immediately they were wrong. Why? Because this is thermally driven flow in a cavity which has trapezoid shape. It has two adiabatic walls, which means zero heat flux, and then inclined walls, one is cold, one is hot. And then the gravity was varied, so it was once in the direction perpendicular to adiabatic walls, one it was in the opposite direction. And what I spotted was wrong is that the isotherms were not orthogonal to adiabatic walls. They were ending at an angle which was like something like 30 degrees. And this was obvious to me that this is wrong, because if you have a adiabatic wall, it means zero heat flux. And zero heat flux is obtained when there is a zero gradient of temperature, because heat flux is conductivity times temperature gradient. So zero flux means you must have zero gradient of temperature. Zero gradient of temperature means that the isotherm must end at a 90-degree angle at the wall. And the upper picture here on the right shows streamlines and isotherms for one direction of gravity, and the lower picture shows for the other direction. It's now not so important, but in both cases you see that isotherms are orthogonal to the adiabatic boundary, and this was important. And the second page shows now what happens when I refine the grid. So upper left picture shows Nusselt number as a functional number of cells. And the middle picture on the upper shows maximum stream function value, which gives you the strength of the vortex as a functional number of cells. And both of these quantities asymptotically approach a constant value as grid is refined. And this is the classical grid dependent study. And I used then Richardson extrapolation to estimate the grid independent values. Then I subtracted value at every grid from this estimated grid independent solution, and then that gives me the error estimate. And then I plotted here on the bottom right error on the vertical axis versus grid spacing on the horizontal axis. And what you see here, when grid spacing is reduced in order of magnitude, error is reduced 2 orders of magnitude. This is what you expect from a method of second order, which means everything is fine. And also this now shows you that the error is lower than 0.1%. And this is now a reliable estimate of the error because you have monotone convergence and everything is fine. Another example here is flow around a cylinder at a low Reynolds number 20, which then produces symmetric solution. You see streamlines on the right, grid on the left. And you also see that this cylinder at a low Reynolds number deflects the flow far around it. What is interesting here is that when you keep refining the grid, that the pressure force reduces as you refine the grid and shear force increases as you refine the grid. And here are shown solutions using 2 different solution methods. One is simple and one is implicit fractional step method. The picture also shows that the errors or the difference in solutions with 2 different solution methods on the same grid are large on the coarse grid, but both methods converge to the same solution when the grid is refined, which is good. And if you look at the total force, which is the sum of pressure plus shear, the error is smaller than in these individual forces because the errors are of opposite signs, and when I add them, they cancel out. And this is something that's interesting. So one needs to look at the components to see really how the errors are. Here is again estimated grid independent solution, and then solutions on every grid subtracted from this estimate and plotted here as error versus grid spacing. Again, you see when the grid spacing is reduced 1 order of magnitude, error is reduced 2 orders of magnitude, which is good. The third example is now 3-dimensional flow. So the previous 2 were 2-dimensional, 3-dimensional flow around the cylindrical obstacle in a channel. So this is channel with square cross section, and I have cylindrical obstacle here. The grid was generated in such a way that I have a smaller CAD for the channel and the obstacle, and now the grid is extruded upstream and downstream from the boundaries of this smaller domain. Because when you do extrusion, you can keep the same grid in cross-section, but gradually expand it in the streamwise direction. And this is useful. This saves computing time, because if I use polyhedra or tetrahedra, I cannot gradually increase them. They are usually of the same size as isotropic. And this is the possibility to make the grid anisotropic. Most grid generators offer this, at least SAR-CCM Plus offers. And here you see I used for polyhedral and trimmed 4 grids with systematic refinement of base size by a factor of 1.5. And for tetrahedra I used only 3 because the 4th one would be then too fine. Here are pictures of what the grids look like. The meshing algorithm was here producing regular tetrahedra and regular polyhedra in the zone which I specified as, you see here a volume shaped cylinder around cylinder and another box behind it where I wanted fine grid to capture the separation and the forces on cylinder, and then coarser grids upstream and downstream. So the polyhedral grid, coarsest one was 366,000 cells, finest one was 10.6 million. trimmed was similar, 442,000 of the coarsest and 11.2 million the finest. Tetrahedral, because tetrahedral smaller, has more cells on the coarse grid, 1.56 million, and already the third grid had 17 million, so I didn't refine it once more, would be too much. What's interesting about this is I start simulation on the coarsest grid, get the solution, then change the base size by reducing by factor 1.5, push button to regenerate the grid. Solution is automatically copied from grid 1, mapped from grid 1 to grid 2, and then I do solution on grid 2. When that is obtained, I again change the base size by factor 1.5, push button to regenerate the grid. Solution is automatically mapped, and so on. And doing so, one saves computing time because every finer grid has now a better initial solution. On the grid 1, I start with constant velocity in the channel, but every other grid has the better estimate. That's why every next grid needs less iterations to converge. And for polyhedral grids, I showed on the left bottom picture residuals for this grid sequencing procedure. And on the right-hand side, finest grid starting with initialization as is done for the first grid with the other procedure. And you see, now it depends on which residual level I want to achieve. If I want to achieve a residual level below 10 to minus 5, this is the blue line which I drew here. So it's 0.1, 0.1, 0.01, and 10 to minus 4, 10 to minus 5. This would normally mean that the error is at least 3 orders of magnitude. So if I extrapolate these residuals backward on the bottom right picture, you would see that starting from the blue line, I would reach somewhere between 0.1 and 0.01, so 3.5 orders of magnitude reduction. So this is something like 4 digits accuracy. That level is achieved with the previous procedure with grid sequencing after something like 75 or 80 iterations. So I start with iteration 500, and this blue line is reached about 550 or so. If I go to a tighter convergence tolerance, then after some time, when I start with the solution from previous grid, the residual reduction rate becomes similar to the one that I have on the bottom right picture. So if I want to go to a very tight convergence tolerance to round off, then the number of iterations wouldn't be very much different. But I save a lot in this initial range. And here you see that also the error is reducing appropriately, because that is what we can estimate from the bottom right picture by this backward extrapolation. So we know that at this residual level, we have also iteration errors reduced by 3 to 4 orders of magnitude. So it is advisable whenever you do simulation to start on a very coarse grid and then go in this direction, because that saves computing time. But also, if I do the simulation only on the fine grid, then I don't know how accurate it is. When I have solution on 4 grids, I can compare them, and I know then roughly what the error is like. Here is just a picture of velocities in 2 sections. So vertical section shows that the flow goes above and below cylinder and has a recirculation in the middle. Horizontal section through the cylinder shows horseshoe vortex. So you see the flow comes towards the cylinder. Cylinder is obstacle, it goes above and below, but because there is a side wall, you get this small recirculation near these side walls. This is the horseshoe vortex that then bends around the cylinder. You will see this more in examples, in exercises, in one other example. Here is pressure distribution computed on level 4 grid, polyhedral upper and trimmed lower. I fixed the same color scale, and now you see what is really the difference between the solutions on 2 different grid types. And when the grid is fine enough, there is almost no difference. Very, very small difference. If you examine every contour line, you will find some difference, but not much. And this is grid dependence of the solution. So for the polyhedral grid, I plot here solution on all 4 grids. And you see grid 1 is the coarsest, is the black line. And the upper picture is the vertical profile behind cylinder, and the lower picture is the horizontal profile beyond cylinder. So once it's in Y direction, once it's in Z direction. What you see in the upper picture is monotone convergence. So you see appreciable difference between first and second grid, but the other 3 are almost on top of each other. On the bottom picture, because this velocity is much smaller, you see upper maximum is 2.4, C is only 0.2, so 10 times smaller, the differences are better visible. You see that from grid 1, black line, it goes to grid 2, blue line, and let's say the left peak above, so value 0.08, it goes from black to blue up and then goes back to brown and then from brown to red. So this is a non-monotone convergence in this case because the coarse grid is too coarse. And in the middle where we have negative velocity, it's monotone. It goes from, but then here the difference between first and second grid is more than 4 times. So this is the irregular behavior because the first grid is too coarse. But then later on, the differences become monotone, and we see that the difference between finest and next coarser grid is very small. Here, solutions from different grids, finest grids, are compared, and for the upper profile, we see they fall all on top of each other. You don't see the difference. This is what you expect. If you go to 10 million grids for this relatively simple case, you should get a solution which is very accurate. The bottom shows the other profile with smaller values. There is slight difference between tetrahedral and the other two. The other two, poly and trimmed, they fall on top of each other. Tetrahedral is a little bit coarser. I didn't have grid 4. That's why there is some difference. But you see, if the grid is fine enough, all are good. Here's another example of systematic refinement. I have to speed up a little bit. This was this U-bend that we showed earlier. And it's the same. If you start on a coarse grid and keep going to the next finer grid, you will get the solution faster. And when you compare the, let's say here, pressure difference between inlet and outlet, you also can see that the difference between first and second grid is large, second to third is smaller, third to fourth very small. You can then conclude how good the solution is. Now, modeling errors are difficult to estimate because you need to know the information of real flow, real geometry, which is usually not available. You need the reference data, which is more accurate than your data. And in order to be able also to estimate modeling errors, one must ensure that discretization errors are at least an order of magnitude smaller, because if they are of the same order, then you can't distinguish them. They can cancel, augment, so one has to make sure that grid is fine enough. And you also have to bear in mind, if you compare with experiments, that experimental data is also affected by errors, and they may go in one direction or the other direction. Now, modeling errors may also affect different quantities differently. So pressure drag, viscous drag, mean velocity, turbulence, everything can be differently affected. So it's not an easy task. And if you don't have data for the problem that you want to solve, you have to check for something similar. Here is another information related to modeling error due to the geometry. As I mentioned earlier, we do in simulation, we use CAD model, which is perfect. Here is from SVA Potsdam, measurement of manufactured tolerance for the propeller. So International Tongue Conference recommends that tolerance should be for model scale, sorry, 0.05 millimeter at the leading edge and 0.1 millimeter otherwise. And you see that this is roughly what is achieved. So the scale is from minus 0.1 millimeter or 100 micrometer to plus. So you see here, when they scan the propeller, not every blade is different, and the discrepancy is in the range of 100 microns. So it satisfies the requirement by ITTC, but it's still not perfect. And what is especially tricky is what's shown in this picture. The black line, so this is the section at radius 0.7 scaled by the maximum radius. The black line shows the cud, and the cud has a very sharp or very small curvature at this pointed edge, leading edge, and then a little bit of almost no curvature. It's better seen on the right-hand side, no curvature, and then again stronger curvature on the upper and lower side. Whereas the measured ones, which they scan very accurately for this radius, they show totally different, nice, mild curvature without any pronounced pointing at the middle. And you also see that in the middle of this picture, both manufactured propellers are thicker than the CAD model. On the right-hand side, you see the grid from simulation, and this grid was aiming to achieve y+1. We'll see later what it is, trying to resolve the boundary layer near wall. And you see that within this difference of between manufactured and CAD model that these three lines here show on the right, I have many cells in my computational grid. So obviously I am solving the flow, computing the flow for a different geometry. And this is a modeling error because when I compare to experiment was obtained for one of the geometries shown on the left, and I'm doing simulation for a different geometry. Another problem is that let's assume that the geometry is correct that I have from the CAD, and I have a coarse grid. So you see here on the upper left picture, when I have very fine grid locally refined around leading edge, I have the very good representation of the CAD model. If I have a coarse grid, then my leading edge looks totally different. So again, when the grid is very coarse, I am computing the flow for a different geometry. And you see on the right, these colored pictures, this is the view from the suction side onto the propeller. And you see that the leading edge is smooth on the upper part where I have fine grid, and it's very rough when I have coarse grid. So again, when I'm now here refining the grid, I see the difference not only between two discretization errors on grids of different fineness, but also two different geometries. And this is then interaction now between modeling error and discretization error. Now, why I take in this case, what is surprising here is if I look at integral quantities, which is thrust and torque, which are basically forces due to force and moment on this propeller wall, they don't differ very much. So difference to experiment is on the fine grid for thrust 0.767%, for torque 2.2%, and for the coarse grid is 0.9 and 2.8%. So there is not big difference in these forces, and this is because these integral quantities come because of random roughness by this coarse grid, that the errors cancel partially out, and then when I integrate over this rough surface, I get something similar as when I integrate over a small surface, but still fine grid is more accurate. If I simulate the flow, let's say around a ship using different turbulence models, then I see different modeling errors. So here, 5 grids we used. The difference between solutions on grid 4 and grid 5 was around 0.2% for standard K epsilon model, 0.7% for another model. So this is the order of discretization errors. And the difference to experiment is larger. So we see that we can now assume that this larger difference is due to modeling error. And what you also see here is that different models will give you different errors. Standard K epsilon model has a positive difference, so it over-predicts the measured force by 1.28%. Realizable K epsilon model under-predicts by 2.6%. K omega SST model underpredicts by 3.6%, and Reynolds stress model overpredicts by 1.8%. So you see that the turbulence models play a role. Another source of error is when we use wall functions, and then if the grid is not appropriate, and we have, so for wall functions, y plus should be larger than 30. If you don't use wall function, it should be of the order of 1. And if I now generate my grid such that the y plus is everywhere around 10. So you see here on the bottom, this color scale, it goes from 0 to 20, and most of the hull surface is green, which means y plus around 10. Then my difference to experiment is between 7.5% and 9%, much larger than when I used y plus larger than 30 in the previous case. So this is something that one needs to take into account. And the final case is the simplest. So we've seen for the ship hull, if I do everything correctly, the errors are between 1% and 2%. I go to straight pipe and make the grid very fine, and I compute fully developed pipe, just straight flow through the pipe. And the grid is so fine that I have 15 prismal layers, y plus is 0.5, and I now take 5 turbulence models and compute the solution and look at the shear stress and pressure drop and compare it to the Blasius solution, which is also not exact, but it's a reference. And once on trim grid, one on polyhedral grid, I see that the difference between turbulence model which has the largest over prediction, which is 3.2%, and the turbulence model which has largest under prediction, which is K omega SST minus 6.5%, I have 10% difference between solutions by different models. And you would ask yourself, well, how can we trust solution in complex geometry when we can't get a solution for the straight pipe correctly? Well, the answer is relatively simple. In the complex geometry, many terms and equations are important, including those which we don't model, which are exact. And when we have simple flow like pipe, many terms which we don't model don't play any role, and the modeling terms are dominant. And this is why here we see the errors from the turbulence models being much larger. Sorry it took a little bit longer today, but this issue of errors is important, and I wanted to be as detailed as possible. If you have any questions, you can ask them now, or you can send them by emails. If you're not in a hurry, I'm available to answer questions now. If your microphone doesn't work, you can write a question in the chat window, then I should see it. In the exercises, you will usually be doing these error estimates will be done in most cases, and we will also request for the exam that when you get your task that you do a simulation on a series of 3 grids and compare solutions so that we see how the solutions change as the grid is refined, so that discretization errors can be estimated. You should also look at the residual reduction, so to make sure if there is a steady state to get converged solution, so that iteration errors are small enough. If it's unsteady, then you have to make sure that inside every time step residuals are reducing, and that you get then a flow which one can interpret physically correctly. Okay, I see one question. The PDF file for Sim 2 is not there. The problem was I didn't know how to insert another theme, and so I put the file into the theme 1. So in the theme 1 you have the third file which wasn't there yesterday, which is the presentation file from today. I uploaded it yesterday, well, this morning at 2 a.m. I think. But I will do one correction because this one, 2 slides, I forgot to text. So as you see, I was editing it late at night, and somehow I forgot to do that. But I will edit it and I will replace it. The rest will be okay. to have the files there earlier, but I was too busy this week, so I managed to upload it only last night at 2 a.m. I think. Any more questions? Well, if not, then we will close it here. And as I said, if you remember any question, you can always send an email to either to me or Dr. Lanterman or Dr. Peters. I guess the exercise will continue after this, and I will now stop my sharing. Thank you for attending, and until next time.
كأنه مفيش محاضرة. والله كذب، والله عودي ما فيش المحاضرة.